Good afternoon, everyone. I'm Apurva. I'm a PhD student at IIT Bombay, and this is week 5 of Stochastic Control and Communication. So, sorry. Um, we'll take a quick recap of what we did last time. Then today it'll be mostly going through what was done in the this week's lectures. I'll slightly talk about a few modifications that are possible, but mostly it'll be a recap of whatever was done in this week's lectures. If you have seen, the assignment questions are fairly straightforward this week, and the content is like that because it was focused on one particular example. Um, I have not tried coming up with more practice examples of that kind. You can bring in numbers and do it, but it's the exact same thing. So that's not going to be the focus. The focus is going to be taking a slow recap. If you have doubts from anything previously or now, you can ask them. Alright, so last week we started talking about what was this dynamic programming algorithm. We said that this algorithm requires us to find out something called a value function, this j of whatever time t. Here we start from the back, meaning we start from time equals to the horizon step, which is n, and we look at what is the value of jn at all the states. And in our case, because we have a special cost or a special reward for the terminal cost, that's what becomes the value function. After that point, it is a recursive relation of this form. Okay, and last time we saw one example, and the example was inventory control. We saw how this idea of DP can be applied here, and that can be used to solve this type of a problem. Today, I'll talk about two different types of problems. In fact, this example of inventory control falls very well in one of those settings, but we'll come to that after some time. Then we went through what is the parallel of this Bellman equation that is written in the form applicable in stochastic control. What is the form of that Bellman equation for a MDP type formulation? So we saw that it takes a form like this. And here there is a policy pi which is chosen for which it is defined. So there are two things. One is the policy pi and another is the value, the state at which the value function is to be calculated. Then I just said it as a statement, no proof was given for this one, that similar to DP, here something called value iteration is used, which basically looks at the max of this quantity over different actions. And if you notice, this is a recursive relation. There is a v of s and a v of s dash. That s dash might end up being the same state if there is a probability of being there. So because this is a recursive relation, it takes care of the DP type recursive relation that we saw in stochastic control as well. So these formalisms are fairly similar to each other. In MDP type settings, there are others which are dynamic programming type algorithms, but there are a few more. I only talked about one of them. And then we used this particular algorithm's idea, and solved an example. And this was an example based on a Markov chain. So very simple Markov chain, and we solved through it. Okay. So any doubts in that?
Yeah,
Yeah.
actually, okay. When we say value function for MDP,
Mm-hmm.
V pi and V pi star are two different. Like V pi star comes when you apply maxima or minima. Like that was the my understanding. But when we see the J function, value function, that itself has a maxima or a minima.
Yeah.
Like why so? Like is it a J star that after minima finding it's a J star or
So okay, so the parallel between these two is right here. So in stochastic control, what we find is some j at time t, and this j at time t for all the x's that are available at time t. Here we end up taking a minimization and maximization is not that much of a concern, because it is only that in one case we talk about reward, in the other case we talk about cost. That's the only reason for max or min. That part is same, but never mind, just let me write it down. To be more specific, it is over pi, or not even pi, it's over ut. So this is
Okay, so this is J star, right? Not J.
yeah.
If I make a parallel with the V pi star, like,
It is. Remember, this was proven
hmm,
in one of the proofs in last week's lectures. It was shown that starting from jn xn, whatever it turns out to be, till j0 x, all the available ones at that point, whatever we get after having solved for this minimization, these are the
mhm,
optimal ones. These are the optimal value function values.
hmm,
So these are actually stars.
okay. And then I had a question on this. Like,
Hmm.
it's kind of a silly question, but I'm not able to make sense. When we reach the last state, like zero state from backward, okay, I have some mathematical expansion
Hmm.
or maybe some policy, but the zeroth state is a random variable, right? Because it can take any value.
Right.
So should we solve for every x zero?
So now it depends. Uh, the way it is defined in MDP setting and the way we talked about even in control, we actually had an initial state. So we had a fixed x0, like it was something. So here we don't need
Okay.
to look at the value of j0 star for all xn. So this was just for the initial state that was chosen in the problem. So if the initial state is not given, then you're actually looking through all of them.
Okay.
But if it is given, then that's the only one that you need.
Cool.
Yeah.
Yeah.
Okay. So now this week, this is going to be mostly using what we learned in DP and apply it to two different problems. So let's just write it again. So from DP we learned that if we want to find the optimal of this type of a problem, our problem was something like this. Uh, so I'm sticking with the stochastic control version. So if it was a minimization of, there is some gn of xn, let me write it as xt. Okay, could be running from 0 till n minus 1. Remember, this is what was the goal in control problem. This is the kind of quantity that we are trying to optimize over, typically take a minima over. And here this u, the action, can actually be written as a function that depends on xk or other things depending on what kind of policy we are talking about. We were focused on Markov type policies, so that's why we have only dependence on xk. So remember, this is still Markov type policies that we're considering, and hence it was an optimization over all of these mu k's. So it was mu 0 till mu n minus 1. There's nothing to optimize at the last step because there's no action available at that point. So this is all we were trying to look for. Okay, so let's denote it by this j symbol. So this is j of not a of, it's just a j. Okay, let's call it some j. Okay, now what DP said was that if we wanted to find the j star, this j star, then all we had to do was do a recursive backward type optimization, sequential optimization. So we start with the last state, which is the nth time step state. So whatever states are available at that point, so x of n, we take the value of this guy, and for this we just take whatever is for all xn. Okay, so this is the step number one. This is looking at the terminal state. Whatever is happening in the terminal state, that becomes the value function at that stage. And hence, the j star at this step gives us the very last point, like how to get to the last point, what is the best way to get there. After that, we go backward and we look at the remaining. So we look at all the other t's which are less than n, and for those, uh, let me not use t so much, I'll prefer using k instead. So we look at k's which are less than n. So for all of them, it's a minimization problem now. So the minimization is at one time at only for one thing. So here the minimization would be only for mu k. So if this k was n minus 1, so I'll be only optimizing over mu n minus 1. That's all. Okay, so this would be gk of xk mu k of xk and wk. This is the stage wise cost, and then there is the value function from the previous step. So the previous step in this case, meaning since we're doing a backward type induction, so here it is k plus 1, and we look at the state there. So that is xk plus 1, and from dynamics we know what xk plus 1 can be written as. So that is some function of some fk that depends on xk mu k of xk, or the action, and wk. And for each of them, whatever we get is the optimal at that point, meaning it's the same idea. So if we had two extreme points, if we had to choose what is the best way to go from point A to point B, and there are more than one paths available, we start from back and say, okay, here we know what is the best way to get here, or what is the cost if we were to get here, which is the terminal cost. Then we take one step back and then try to see how to calculate a quantity like this, and which action minimizes that quantity, as in from this node what is the best possible way to get to the last extreme point, or from this node what is the best possible way to get to the node B, and so on. So here from each of them I have only one way of getting, right? Maybe there's another path, something like that. So it looks at the optimal at each of these sub problems. In that sense, we get all of these to be the optimals. And then once we have all of them, meaning we have managed to find what should be mu 0 star. Okay, we start the other way around, right? We start from n minus 1, n minus 2, and so on till mu and mu 0 and all of that. And hence you would have found our optimal policy. That's what we do in DP. That's what we've done in the previous week's examples also. So this week also we'll continue the same thing and focus on two specific examples. Anything, any issues so far? Any doubts?
No.
Okay, perfect. All right. Um, so in the last week's lectures, one of the topics that was covered that we didn't take in the tutorials actually was this optimal stopping problem. You can think of an example and then come back to it. Uh, in the lectures, they've talked about one particular example. I'll talk about another one so that you have a breadth of idea. So think of a trading type situation. There, there are a lot of things that affect the market. Say, let's say you focus on one stock at a time, and you've already bought that stock, and now you're just supposed to decide whether to hold on to it or sell it. If you hold on to it, then you're still a part of the process, and that particular the value of the stock is getting affected by a lot of other factors which you actually have no control over. On the other hand, if you exit, you are out of it. Behind it, the state might still be changing, but for you, since you have already gotten a reward or a cost out, you're done. In this problem, you can think of the background thing as some sort of a Markov chain that is continuing. As in, if so, we can focus on any one stock at a time, right? So, there may be factors that affect that stock. Maybe they released their quarterly or annual performance reports, and people had some expectations for them. If the expectations were met, a certain direction of the stock prices would happen. If not, something else would happen. Maybe a third factor came in, maybe some policy updates were made, maybe in the country, maybe outside the country, and so on. So, all of these things which are happening are actually things that can be modeled into a Markov chain, to be more specific, into an MDP. And the states can be thought of in this particular example as the different values of the stock, whether it goes up or whether it goes down. Okay, now this is a slightly more complicated example because now I'm saying the state space is actually not finite. In the example that sir talked about in class, the state space was taken to be finite. Okay, so now in a setting like this where we talk about optimal stopping point, as in when to stop, when to stop being a part of whatever that problem is, whether it is to decide when to sell a stock or when to even enter a market. Both of those are opposite situations, when to enter or when to exit, so trading type situations. That can be modeled into an MDP and hence can be solved, or we can come up with some sort of an optimal answer using Bellman equations, or DP type algorithms. Okay, so this is some of the stuff that I've just taken down from the notes directly. So I'll quickly brush over these. So we'll be focusing on situations where the state space, for example, the market, has a state space which is finite. And possibly something that is getting affected by time. It's not stationary, it's not stuck at one value for too long period. So because we don't have a way to affect the Markov chain or affect the market much as a retail investor at least, this is going to be an uncontrolled Markov chain, something that we have no control over, as in none of our actions would change the Markov chain itself. Our action is limited to whether to continue in it, as in just hold the stock, or sell it. Or from the other perspective, when you're deciding when to enter or not enter, it is to enter or not enter. So we have two options of becoming a part of the MDP or not becoming a part of the MDP. That's about it. So for us, the two actions are whether to continue or to quit. Let's say when you decide to continue in the market and you see that the price is going up, but the growth of the price is, steady, it's not too sudden or something like that, then there is a certain cost. The cost is in the sense that you have invested some money. If you had invested it somewhere else, maybe you would have gained more. But here, because you have invested in this particular stock, you are stuck. You can't just sell it off directly because you chose not to sell it at the current time period, maybe at a given day. Then you you would incur some cost. That cost might be regret, or maybe we're quantifying it in terms of a number. So in that sense, we're calling the cost as CT of S. T being the time step, S being the state. On the other hand, if you decide you've reached a situation where the stock price has reached a certain level and you don't want to continue in that anymore, you could exit out of it. And once you exit out of the stock, depending on what your stock's value was when you bought it and when you exited, you'd probably get a reward. I'm assuming that you're not booking losses. You're more interested in booking profits, which is which is typically the case. So that could be, you'd end up getting a reward RT of S. Now S depends on the state. In our particular example of when to exit the market, S depends on the average value of the stock that you were holding. So it would depend on that and also the current value of the stock right now. So it depends on two things. So this is slightly more nuanced example.
Sorry, could you repeat the last one?
So here I'm saying it depends on state, but in the example that I'm talking about, the example of trading, the reward will depend on what was the cost, what was the value at which you bought the stock price and at what value you sold it. So it's going to be just the difference of those two.
The delta.
Yeah. So in principle, it depends on both of them, right?
Correct. But here we will have one more option, right? Like entering in the market.
So I'm assuming you've already entered the market. That is
Okay.
one problem. The other is deciding when to enter, which is like the reverse of this problem, but the same idea holds.
Okay.
Alright. Then next thing that we worry about is that there is a time horizon, that this is a finite horizon problem, and there'll be a terminal reward. Like if you just let the stock be, let's say it's a intraday trading, okay? If you do not sell it during the day and you do not decide when to sell it, it'll be just sold off at the end of the day at whatever value the stock price was. So that will give you some reward. It might even incur a cost, but let's just call it a reward, and that is H of S. In the example that I'm saying, again, it'll depend on the initial S0 you started with and whatever state or whatever stock price it is at right now. Okay. Okay. So did mention that one of the examples could be in finance, in option trading, or in finite horizon problems. Okay. So this particular problem is as follows. Maybe I'll try these things again. This. Okay. So we have, if we were to be formal about all of this, now we're mapping it into an MDP. So our MDP requires a state space, an action space, to be more specific, some probability transition probabilities. Okay, we're denoting them by probability for P. The reward function r, and the time horizon t. So let's say the number of epochs it runs for is n, so it runs till n minus 1, and by then you have to decide whether to sell it before, or it will be by default stopped at some value. State space is, now here we are taking the state space to be the s dash, as in the evolving states, and along with that the stopped state, the mdp once it is stopped. So in case of a market, even if you exit the market, it actually doesn't stop. But by delta s, we are actually referring to the state when it stopped, and after that we are not looking at the market again. In the example that will be talked about further on, the secretary example, here it makes a little bit more sense, this delta s. Okay. Now action, we have two types of actions available, either to continue or to quit. So we can say either to continue, so that could be C, or to quit. Both of those actions can be done when you're in state S dash, meaning when the market is working on its own, or when the state is evolving. But once you have reached the delta state, or once you have reached the situation where there's no further change, you've already quit and you're out of it. Beyond that, you don't technically have any action available. You do, which is, this is just to model it properly. So we say that you can just continue, you can just let it be. Now, next part is to model the reward. Now, the reward will differ in what situation you're in. So, if you're in the S dash state, meaning the MDP is going on, it's ongoing, and you have decided to continue, and it has not hit the last terminal state, meaning you'll incur a cost of being a part of it, or you'll incur a cost of just being in the market, in the sense you lose other opportunities. So that we are writing as minus of ct of s. You've already taken into account which action was taken, so that is already taken care of. Another option is when the state is again in S dash, but the chosen action was Q, meaning you have decided to exit from the MDP.
One question.
Hmm.
This reward function, why it is not depend on the next state? Because next state quitting and continuing will have different consequence, no? Like S comma A comma J.
I think this is just talking about the expected reward. You can take expectation over the next J's, because we have the transition probabilities. So
Okay.
it, you can think of it like expected reward if that's the kind of reward you want to talk about.
Okay.
Hmm. This is something that we saw even when we were looking at those small Markov chains. We had the
Yeah, I
two
was
versions.
inspired that only.
You can go from one to another. It's easy to go from one to another. So people define it whichever is the more convenient and easier way.
Okay.
All right. Then, right. So the next situation is if you decided to quit. The MDP was going on. You've not hit the horizon, and you decided to quit. So you decided to get some reward out of it. So let's say that reward is some RT of S. And the last scenario is once you've already stopped and the state happens to be the stopped MDP, or the MDP that no longer matters to you, there's not going to be a reward or a cost per se. So that can be thought of as just 0. And we can have a terminal reward. I am not able to recall How did sir define the terminal reward in the lectures? It can be anything. There's no. Oh, okay. We did define it. Ah, right. So it was this h of s.
Yeah, zero.
It
It's,
depends. I think
yeah.
in the problems he took it to be zero. In one problem he took it to be zero. The other problem had okay h n of s or whatever h of s. Then, like I said, since we are talking about an MDP, we need all of these quantities, right? We need all of them. So we also need the transition probabilities. So the transition probabilities in this problem can be defined quite simply, that if you are in state S dash, meaning the MDP is running, and you know that the next state is also in that only, then what is the probability of continuing? This is the standard probability. There's nothing special about this probability. This is something that we can choose what it is. On the other hand, if the next action takes you to, if the next action basically is to quit, so the next state ends up being the delta state, where for us the MDP has stopped, then the probability of the next state being that delta state is just 1. For it not being this delta state is just 0. Or in the other sense, if the MDP had already stopped, meaning we had already sold our stocks, then none of these probabilities matter. But if you were to write it more carefully in a complete sense, then the probability when S and J are both in the delta and the action chosen is to continue, then we'd get a probability 1, else we'll get a probability 0. So there's like a self loop there. Okay, this is just description of the problem, nothing else. This description can vary depending on what kind of a problem you're talking about. Okay, so this was the optimal stopping problem. In the optimal stopping problem, we have a MDP running on its own, and we are supposed to model it into an MDP and then use the tools that we have, which is the Bellman equation or the DP algorithm, and solve for it, solve for the optimal case. So one particular example of this, and this was covered in lecture also, is the secretary problem. This basically says, suppose you have n candidates, they come for an interview one by one. The catch here is, once the interview is done, the interviewers need to decide whether they're going to place and give that candidate an offer or not. Depending on whatever was the performance in the interview, they're supposed to make that decision. But also, they're supposed to consider this fact that once the candidate leaves the interview without an offer, they cannot be made an offer at a later time. Typically, in the standard scenarios that we see, the interview scenarios, the offers are made at the end so that they can compare all the candidates. But here, let's say they're supposed to make the decision online or on the fly. So, based on what they have seen, they're supposed to now finally decide whether to give the offer to a current candidate or not.
So
So,
basically, this is not history dependent, but real world will be history dependent.
real world would look, so in real world, offers are made this way in placement scenarios a lot of the times. But if you're going for a normal interview, then they look at all the candidates and then decide whether to give it to a particular candidate or not, depending on the kind of candidates they've seen, what they expect, and so on. So here, obviously, we're trying to model a simplistic version of that. Okay, so here, ultimately, the goal is to maximize the probability that the best candidate gets selected. So we can think of it this way, that from the set of candidates that are present, the n candidates, there is a true preference ordering. As in, there is someone who is the best for the particular role, and then there is someone who is not. So there is an ordering in the preference. But this actual ordering is not known to the interviewers at any given point of time. What they can know based on the interview that they saw, whether this candidate that we saw right now is the best so far, and they're supposed to make their decision just based on that. So they can see whether this is the best candidate so far or not. So it's just these two scenarios that are available to them, right? So the modeling of this problem is this way. There are two options. The state can either be 0 or 1. 0 or 1 here means at that particular point of time, this is the best candidate. Best candidate so far. The word so far is important here because they can't have a hindsight information and they can't make their decision based on having seen the whole set of interviewees. They are supposed to make the decision on the fly in the let's say the interview hall itself. So this is the keyword here. The other situation is if not.
Okay, if I try to correlate with the previous lectures, in this model is a pure history dependent model, right? Because at a particular time t, I know the previous S states and actions also because continue.
It's not like that. See, the state itself is such that it has some information that correlates to others, but it is still one state. I am still not looking at all of them. The
Okay.
policy that is to be done, so
Mhm.
history dependent or not history dependent, comes at the level of policy,
Oh, yeah.
right? That is still our choice. Are we going to look at candidate 1, candidate 2, or candidate 3? See, let's say I am at the third candidate already, and do I look at all of them or do I make my decision based on the third one? I would have noted down something about the previous ones. So I would already have a rough idea where this candidate stands as compared to the previous ones. Right? So do I
Okay.
need to go back and look at all of them or not? That's all of that information in this particular modeling is already contained in this S. The way we have defined this S dash actually. Followed? So, in some sense, the state itself has uh, some history type knowledge. Okay. So, in the modeling, next step would be to talk about what are the actions. Okay. The actions are A of S. The actions are whether to give the offer or not give the offer. And that is for both 0 or 1. So, this is true for both S that belongs to 0 or 1, and this is true for all times also. So, how did Sir do it? Did he call it? Did he give it some names or don't remember? Okay, maybe
We can use our notation.
we can. We can.
No problem.
There's no harm in that. We don't have to worry about it too much to be specific. So we can use the same notation as the previous example only. It's, so if you're in the stop state, like if you've already chosen your candidate, then there's nothing more to do. This is assuming that let's say you're choosing only one, you're giving offer to only one candidate, or yeah, the budget is not defined, so let's say we're talking about only one candidate. So after that you just continue. But if the budget was defined and you actually were, it was possible for you to choose two, then this would need to be defined in a slightly different way. Okay. Then right, then comes the cost. Now let's say the problem is,
In this definition, is it something missing? Like AS is equal to C comma Q for all S belongs to A1 only, right?
hmm? No, no. Whether the candidate is chosen or not, no, sorry. This S tells us if the candidate is the best so far or not.
Mm-hmm.
Whether that candidate is chosen or not is still an action to be decided by the interviewer. So that's what the C or Q means. Q means to give an offer. C means to let it go. Let's look at the next candidate. So in that sense, so this is giving the offer. Uh, if an offer is given, then the queue of candidates might still be there. So for the remaining, what to do? There's nothing to be done. There's no more offer to be given. So it's the problem is actually over. The catch here is the candidate who got the offer, is that the best one that who could have gotten the offer? Could there have been somebody else who was better than this one who could have been given the offer, or like what is the optimal policy in a situation like this? So it could always happen that in the hope of waiting for a better candidate, the interviewer might, look at a lot of really good candidates but be like, no, 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 there must be someone even better. So in the hope of looking for a better one, they might actually not give an offer to anyone before, and the last candidate ends up being, well, not good enough or not that good. So such a situation can clearly happen. So the problem is to figure out, uh, or the goal is to try and maximize the probability that the candidate that is selected is either the best one itself, or at least as close to the best one that is there. So from the way we have talked about the problem, there is a candidate. So let's say, uh, maybe we can pause here, take a slide example, and then continue. That's okay. So let's say there are total 10 candidates who show up for an interview, okay? There's a true ordering. So let's say these are the candidates, and their true ordering is this one is the best. So this is the ranking I'm giving. One means better. One, two, three, 4, 5, 6, something. Something like that. This is just one possible ranking. The ordering could have been different, the rankings could have been accordingly been different. Now, in all of those scenarios, there are way too many scenarios of that kind, right? There are 10 positions, 10 candidates to
Mm-hmm.
be moved around. So there are 10 factorial possibilities of different kinds of arrangements of just them,
Correct.
right? Now, which one should they be giving the offer to? How do they know that they are making the best possible thing, the best possible decision they can make in every one of those situations, not in just one of them, not based on knowing something about the sample that they're seeing? So their decision can't be that they give it to the very first person. They don't know if that is the best that is there. First will by default be someone with the state s equal to 1 only. Right? There was nothing before first, so he'll be the best. So would you just give it to him only, or would you wait to see a few more and then decide what to do? So that's the structure of the problem.
So basically, initial state is one.
Yeah. The way the problem is defined, S0 has to be 1. Then onwards, It can be anything. Actually, for the first one also, it could be zero, that it's the worst candidate. It should not have ranking or state equal to zero. That's decided on how the ranks and states are correlated with each other. What is the main idea? Like if the ranking is this, more than 50%, better than this, then we give a ranking of this kind, or what? Like a tie breaking rule will decide whether it will be zero or one. But for the remaining, it's completely random.
Okay.
Okay, so where were we? Right. So the modeling requires us to talk about the state space. The state space here refers to the some information about the ranking of the candidates seen so far. Then AS is the kind of actions that can be taken by the interviewers. Then there is some cost. So if a candidate is passed on, like not chosen, then we are saying that there is no cost. There could be. The problem could be in such a way that there is some cost, there is some positive cost. But in this particular example, let's say there isn't. Then further on, the reward is of this kind. If the candidate is not good enough and let's say gets chosen, so candidate S is, the state of the candidate is S0, and it gets chosen before the horizon is reached, then the reward will be zero because they didn't get the best possible candidate. We know for sure that the candidate that they got is not the best because the value of S is zero for that candidate. So by default, there is no reward in that. Now, since we know that there is no reward for this, we would try to not reach this situation. Or, in some sense, it's saying whatever optimization we do, whatever the algorithm gives us, at the end it has to be such that for s equal to 0, do not stop. That will be the default thing to do, no matter when it is, no matter at what time step it is. The best thing to do when you're seeing a candidate who is not the best so far, that candidate should not be given the offer. It is simple. On the other hand, if you see a candidate who is the best so far, meaning, for example, if this was the scenario, right? So, first is not the best so far, okay. You went to 2, this one is definitely the best so far. You could now decide, should you be giving offer to this candidate or not? Then maybe you decide not to and then go on further. So, the way the reward is defined here is amongst the candidates that got chosen. So up till time t candidates would have already shown up. So in those, the ones that got chosen, is there a probability that the best candidate showed up already or not? That's the reward. That probability is the reward because ultimately we are still interested in just increasing the probability of choosing that best candidate. So here, the best candidate is the sixth one. Up till here, the best candidate has not reached. After this candidate reaches, all of these will just be of state s equal to 0. But if this is passed, then the reward will be 0. But up till here, there might still be some reward because the best candidate is not reached, but there is still some possibility that the best candidate is still out there. Okay, so that is what is captured by RT of 1, state s equal to 1. And this means we are actually referring to, from the set of candidates, what is the probability that the chosen subset, the subset T, so this is numerator and denominator, both the things. So what are the different ways of getting a situation where the subset T out of n, of T size out of n,
But this could be a fixed number, right? Why are we connecting with probability?
Oh, that's just how we have said that that's the goal we want to focusing on. There could be a fixed number.
Okay. So it's just an imposition by
It's
this
an
problem
imposition.
solver.
See, think about it this way. When a company is trying to hire employees, they want to hire the best one that they can from the pool that they got. Right? They don't have the resources to go back and look at each candidate that they received. Let's assume that's the reason and that's why they have to make the offer then and there. So they would want, if they are investing in getting a new candidate, they would want to stop at the best possible situation. Even if it's not the best, at least stop at somebody who is good enough. So best so far. So if they saw 10 candidates, total 10 candidates, and they are at candidate 5, and they see that candidate 5 is the best so far, it's a good idea to choose that candidate. As in, it depends what that number is, after how much fraction they've seen, when should they actually stop. But
Mhm.
that's roughly the idea here. This problem will actually give us at what fraction they should stop. You can think about it in a slightly different way and wonder, if you're sitting for placement, what number should you not go to. If you go after that number, you have a very good chance of getting selected. But if you
Definitely
go,
not one.
definitely not one, and definitely not last. Both of those are very risky. Somewhere in between. But okay, the catch here is, right now the problem that we are solving is such that uh, there's only one candidate to be given the offer. If it's more than one candidate, it's a slightly more complicated problem. And there might be nicer and more intuitive, actually, this one was also intuitive, but there may be more intuitive ways of dealing with these. That might still give you an intuition, but nothing more than that. Okay, did that answer your question properly?
Okay. Yep.
Alright. So we are interested in looking at the subset of size t out of n where the best candidate is present. And we're dividing that by the denominator, of all the different ways of getting t candidates out of n. So it's just n choose t. From n, you're just choosing t, different ways of choosing. But here, if it is you want the best candidate to be included, means that is one you're choosing by default. It's the remaining you have a randomness over, or you can choose one of them. So here it just means you're looking at n minus one of them. One you've already chosen, so that becomes the probability one thing. CFT. So this,
T minus 1.
hmm?
T minus 1, no, because one position gone. So n minus 1, C T minus 1.
Right.
This formulation makes sense, but I'm just wondering some other extra formulation anybody can impose and let's see the performance. Will it be same or not? Or fixed number?
It will be very hard to do in other cases. There's a
Okay.
reason why this problem was shown in class, and why I'm saying that it's very difficult to come up with problems that can actually be solved. You
Okay.
can come up with modeling constraints and so on, but typically most modeling constraints would be very difficult to solve or get even an approximation for. They'll be research level type problems, like they'll require a lot of work to do. So for illustration purposes, uh, it's just simple problems. But otherwise, see, just like you were saying, right, this is a problem with offer given to one person. You could be like, okay, let me just expand it one step and say I'm giving offer to two people. So from my pool of candidates, I want the first one and the second one, whoever has the first and the second ranking. What would happen to the whole problem then? How would you solve it? You have to use the same logic, same reasoning, but because of the complexity of the problem, it increased right away, right? You have to now define the state space more carefully. You have to decide what the actions are supposed to be. So the whole process needs to be done just more carefully. That's about it.
Or
It's
or
doable.
we can divide into two Markov decision process. Like first decided, after that there is another Markov process for choosing one only. Like that two candidate I need to choose. First candidate decision I'll take one Markov chain. Once I decide it, next will be another Markov chain, the same type.
No, 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 not like that. See, you're not going to see. This is the pool of candidates you're going to get. Okay. For example, now if you don't have a plan, you're going to keep getting candidates one after the other. You have to have a plan of which one to choose, in what situation to choose that candidate. You can't have them give you two interviews. Having two MDPs is like giving you two interviews. It's in one MDP,
Uh,
in one go only you have to make that choice, but you have to choose two people.
Correct, correct. But I'll choose. I'll run the one NDP. Once I decided one candidate,
Then
my
it's easy. Once you've
uh,
decided on one candidate, then the second one just boils down to the same situation that we have
same
here.
problem. Yeah, exactly.
But now you're not interested in choosing the best one. You're okay with choosing the second best also. How do you define the second best? Meaning, your state space can't just be 0 and 1. It needs to have that information also. Is it the
Okay.
best or the second best or none?
Means zero, one, two.
Yeah, so in that sense, it has evolved. Then now your action space hence would also need to be rewritten and thought about. Following. So it's doable. I'm not saying it's not doable, it's just a little bit more harder. Other variations could be that there could be a cost of letting go. So there is a cost of time. You interviewed a lot of candidates, and maybe you couldn't choose any one of them, or you just were struggling to choose. So there is a cost of time, of resources that went into taking those interviews. So this could be a negative value, this could be an actual value, and it shows up in the whole problem. That's another variation that you could try out. Okay, let's continue with the one that was there with us. So finally, what I'm saying is this RT of s equal to 1 is t by n. Okay, now this was just an example, so let's leave it here only and continue. So what do we have so far? We have the state space, action space, the reward function. Next we want to talk about, right, we have to have some terminal rewards also. Okay, so if what happens is that at the end you ended up choosing the person with whose state was s equal to 0, meaning you definitely didn't choose the best one, then this has to be 0. The probability of choosing the best one is what we were putting in reward, right? So you've definitely not chosen the best one, so it is 0. But if you see that h, the state at the terminal point, is 1, meaning that is the best one so far, and you've seen all the candidates, so you actually managed to choose the best candidate, so the terminal reward here is 1. Okay, now next we have to talk about the transition probabilities of this problem. So let's say for each time t, we're writing the transition probabilities as this. So this says if you started in some state s, the states are the kind of candidates that are there, some action was taken, either you decided to continue or not, and the next candidate came. So, what is the probability that the next candidate who came up has state value s or s equal to 0 or 1? So, the thing here is what is the ranking of one candidate doesn't really depend on the ranking of the other candidate. It is quite possible that the candidate that we got at time t minus 1, which is representing state s, could be the best so far. So it could have s equal to 1. But just because this one was best so far doesn't mean that this can't be even better than that. So it can be better than this or it can be worse. It can have both the possibilities, meaning J, the probability of getting a candidate with some state J doesn't depend on state S at all. It's just something that depends on J itself.
Yeah, I had the doubt in this. Even in class, sir gave same logic.
Ah, okay.
But if you see, this is a Markov chain probabilities, not Markov decision process probabilities. If
Mm-hmm.
you go to Markov decision the Markov decision problem probabilities, there are actions involved,
Hmm.
and definitely J is depend on action, not the state. I agree, but because actually PT J given S comma A, that A has we have quitting and continuing. At a particular state, I can choose action, continue, and quitting, and it depends upon it will create J.
Hmm.
So I had doubt, but I thought sir is going on with. I really thought like next session sir will explain that.
Uh, okay, that's a fair point. This is so typically. So what you're saying is typically the transition probabilities are of the form J given S and A.
Yes, and I agree J does not have anything to do with S, but definitely with A. Because if you continue at a particular
Okay,
state,
I
J
think
will
there might be a by default assumption here. Let's look at it carefully. I think we can figure this one out quite easily. Okay, let's do this. So let's focus on the case. See, continue is an easy case, right? If A is continue, it's easy,
correct.
right? The next candidate will show up. The next
Will show.
candidate who shows up has nothing to do with the previous candidate, correct?
Yes, correct.
So you have no issue with the case when A is equal to C, meaning you do agree that this is the same as PT of J given S, which we already understand that has no dependence with even S.
Perfect.
Perfect. Right. What about when A is equal to quitting or an offer is given?
In that case, the probability of J is equal to 0 should be 1, right?
No, so an offer is given doesn't mean there is no other candidate, no other better candidate. You chose to give an action. I am not saying that's the optimal action. That is just an action.
Mm-hmm.
If you just took an action, the next state could be anything. But
Correct.
because you've already given an action, your next J is no longer in the same 0 1 situation. It's the delta now.
Delta,
So J
yes.
is by default delta. That's a different situation altogether, right?
Okay.
So I think that's the reason why it was okay to not have to worry about it. So let me write that here. So if J is delta, then this probability just becomes 1 because that's where you'll be, else it's 0.
Hmm. Got it. So
Right.
basically, we are just only continuing on.
Hmm. This is enough to talk about transition probabilities because the actions are so simple.
Okay.
Okay, you can think of it this way. At times when people are supposed to make offers, for example even in interviews, what they do is they have straightforward acceptance and rejection, like right away they decide whether to give it to somebody or not give it to somebody. But there may be situations where they're a little confused. Should we be giving offer to this person or not? This person seems decent, good enough. Should we be giving an offer to this person? Meaning there's a third action involved. There's like a wait listing. This happens a lot of the times in many different interviews. It happens even when you give interviews for admissions to universities and so on also. They have a waitlisting. Then from the waitlisting they decide, but then they're looking at the whole history. But whether to put something in a waitlist or reject, that is also a decision to be made. So maybe if we think about it that way, if we had a situation of adding one more action, whether to put it in the waitlist pile, then we might have to be more careful how to talk about transition probabilities, because then it may not be so straightforward. Then there might be more details, more complexity here.
Hmm. Okay.
Okay, I think the speed with which we are going, we might only cover one example today, but yeah, I think it's better to be detailed and thorough than rush through it. Is that okay?
Yeah, perfectly fine to me.
Yeah. Okay. So now we are going to talk about these two probabilities. If you don't have a doubt, we can skip this part. Otherwise, we can talk about these probabilities. So, okay, okay, yeah, yeah. So, what is the probability that the state is 1 at any given time step? The time step, it, the relevance of the time step is a little bit only here at this point. Hmm.
Same logic, like
It's the same logic, yeah.
at T, yeah, at T, the best candidate is there. So total permutation, and then you fix one candidate and previous permutations.
So, if you've seen the best candidate, so that would be this is just arranging t items or t plus 1 items, right? That's about it. So this just turns out to be uh, t factorial divided by t plus 1 factorial, or just 1 by t plus 1. And yeah, this holds for all values of t. The t values were from 0 to n minus 1. Yeah. Okay. Now, what is the probability of pt being the state being 0? That's just the other way around. So that is 1 minus of the previous one, which is t by t plus 1. Okay. So this is just writing out the same thing again. Skip this portion. So in this sense, sorry, excuse me. In this sense, we have the transition probabilities just in the form of these two. Next, our goal is to optimize this quantity. What is this quantity? This is the overall reward. The first term is the terminal reward, and this is the reward in the other cases. And the idea is to just maximize this. That's a typo. It's to be decided based on the ATs, or rather A0 till A n minus 1. What action to take when. Okay, so now we're just going to apply dp to this problem. And applying dp means we start with the terminal state and then go backwards. Now, for the terminal state, what did we say about the terminal state? Okay, these values are already fixed. So the process of applying BP, we would have Jn of xn. If xn or the state was 0, we would be getting just 0. If on the other hand the state is 1, we would be getting 1. And there is a third situation. What if it's the delta state, meaning the offer has been made? So it's this one, Jn of delta. If it's Jn of delta, then there's no real reward or anything. It's already over, so there's nothing further that happens, right? That's what we said when we talked about the rewards here. Oh, we didn't specify it. Okay, never mind. So this will be 0. Okay, next step we would be using the DP type algorithm, and we'll look at the remaining ones. So we'd be interested in looking at for any t less than n, this particular quantity, J t of whatever states are possible. So now I'm going to call the states as st rather. So here we are interested in maximizing. So this becomes a problem of maximizing, and there are two actions, whether to continue or to quit or make an offer. And what are we maximizing over? So the maximization is over the cost, this ct of st, whatever that was. So first we're writing the stage wise cost or reward, whatever that is, rt of st, then whatever happened in the previous step, jt of jt plus 1 of st of 1. And this pretty much is the same as saying, so we can write down what this is for the two situations. So okay, let's do that first. Right, so what this means is we are interested in ct rt, this is the stage wise reward, if action c is taken. So this has the form of, this is a max between, if it's continuing, so this term is there, this term is there, and now this term, the last term, this is pretty much something like an expectation of a reward, like whatever happened in the previous step. So this can be thought of, now this is something that I'm taking from the MDP formulation. I'm just directly taking that here. So there is the transition probability. Okay, maybe I should show you what I'm talking about. Right, you remember this form, right? There is the first term, which is just the expected reward, and there is this expectation,
Yes.
right? The previous j's with the transition probability of that. So this is the extra component that I'm considering. this whatever reward cost stage wise, I've already considered that. This is the next term. Okay. uh,
Yes.
so that becomes so the probability, okay, pt of j given s for the state j. So this j, this is the next state, right? This is the state that I'm going to have here also in jt plus 1. So now st plus 1 is just j. This is the part, this is the extra part. Okay, wait a minute, this is a little unclear. Okay, sorry. Here, depending on what action you choose, you don't get both of these together, right? If you have chosen to continue, you don't get a reward. But if you have chosen to quit, that's when you get this reward and you don't have a cost. So those two should have been split up. Right. So let's say first I'm talking about continuing, meaning there's just a cost, nothing more than that, and the cost is this way. This is the cost. Ct of st is the cost. While this is the extra term, the expected reward that you would get for continuing. This is one scenario. The other scenario is if instead of quitting you decided to, so an offer was given, so what you would end up with would be rt of st. That's first term. Second term is if you have already quitted, then there's no next state to go to. The next state is just jt plus 1, and from this whole s equal to 0 or 1 you go to the delta. That's all that is there. So this is how it will be written. Making sense?
Yeah.
Yeah.
Now st could be 0 or 1.
Hmm? Huh. The j could be 0 or 1, s could be 0 or 1. Okay, so let's write it out carefully. So now if we are more interested in the situation where s is equal to 1, then this is a max between ct of 0, sorry, ct of 1, s is already chosen to be 1, and this probability can just be written as p 0 of 1, which means j is chosen to be 0, that the next candidate who comes up is not better than the previous one. So j t plus 1 becomes, we take off 0, and the next would be the probability of going to a candidate with which is better so far. So j becomes 1 in that case. We take jt plus 1 of 1. This is one scenario. This is if we are letting the whole thing continue. We're letting the NDP continue. That we are still going to look at the next candidate. Okay. Then the other situation is much simpler. It's just the reward of having chosen that candidate, and since the candidate has been chosen, then the only option left is to go to this the ending state, so what we call as the delta. This is if we started out from state 0, or we took s equal to 1. The other scenario is if s was equal to 0. The only thing that changes is over here. Okay, we'll come to all of these things. Fine. So here now notice the way we've defined CT, this is already 0. So there's nothing to worry about. This is 0. This anyways just goes away.
Reward
RT,
for continuing is not there, right? Only cost for continuing.
sorry?
Reward for continuing action is not present, only for
Yeah,
yeah.
yeah, yeah. Yeah.
Okay.
That's why earlier by mistake I'd written RT here,
Mhm.
which shouldn't be there for continuing. So removed it. Okay, now recall what was RT of 0. Did we have something?
0.
Yeah, so this also goes away. This also goes away. So now it's the remaining terms that we have to deal with. Um, let's focus on this state. This state. So we know Jn of delta is 0. From Jn to any of the previous ones, t n minus 1 or anything else, there is no action that can be taken. Right? See, here we're writing j's for these because there are two actions that can be taken. Here the only action is to just continue. So whatever we get is to be continued. There's nothing more to do in that situation. And because there's no choosing happening, this will just continue here also. So this will be again 0. And this goes on for all t. Is that clear? So it's the same logic. So typically here we were able to do all this because we were taking a max over two values. In case of delta, there's nothing to take a max over. There's just one action which is to continue. If we were to continue with that action,
But
we
we
would.
have continuing cost, right?
But okay. So okay, let's write it down. All right, not an issue. Jt of delta we're writing, and we want a max. So there's no max here, so there's just whatever it comes out to be. There's Ct of delta. We've not defined it, but we can say that that is 0.
Yeah, plus expectation of the
Yeah. So there could be, if you are in the
whole.
delta state, this, we've not even bothered defining these. Let's say we did we defined these. So there's some j we go to as a next state, as in the, let's say there's a situation where the mdp continues. Here what we're talking about is mdp stops. There's no more interviews happening after that.
Mm.
But let's say if that's not what we are talking about, even if we were to write it down, then what we have is jt plus 1 of the next state. But in reality what happens is, if you are in the delta scenario, you will end up staying in the delta scenario. So this j is actually just over deltas.
Why? But
It
we
has
have
stopped.
taken action of continuing,
No,
right?
but it has stopped.
So only one candidate we are choosing. That's why.
Yeah.
Okay.
So
So this
because of
probability
that,
is zero.
fine, this can have some probability being in the state delta, but this is zero, right? It is 0 for n minus, it is 0 for n. Because of that, it will become 0 for n minus 1. It will become 0 for the remaining ones subsequently. It's because of this being 0 and this being 0.
That being also zero because j given condition the delta,
Mm,
probability of j given delta. So delta after that you won't come any state.
exactly. So you
Okay.
could have taken this to also be 0. So because of that, we're not worried about this part at all. And hence, this term also becomes 0 in both of them. And we know these probabilities, right? We know what these probabilities are. Probability of
Yeah.
0 or probability of 1. So if I were to write it out, so jt of 1 is max between, for 0 the probability was t plus 1. Is that correct? Yeah, I think that is.
Yes. Yes.
And this was 1 t plus 1. Okay. Right. This is scenario number 1. The other scenario is, what is rt of 1? We had a value for it,
T by capital N.
t by capital N. So we have the whole thing, t by capital N. And notice this jt of 0. Now there's no, okay, let's write it out, then we can argue again. It's this quantity as it is copied, right? This quantity and this quantity is the same because it doesn't matter what was the state it started out with.
Hmm.
Hmm? So this quantity and this quantity are the same, and here, sorry, this quantity has become 0. So for jt of 0, the max is between this and 0. And because all of these jn's, the terminals, are 0 or more, we can argue that this quantity will always be greater than 0. It could be equal to 0, but this would be greater than or equal to 0. So we don't need to write the max, and we can just say that this is exactly this quantity. Acceptable?
So basically, the logic why it is equal to zero or greater than equal to zero, that is not digestible. Like basically, idea is like at nth point,
Hmm.
I'll reach either zero or one.
You'll
So when
either
I go,
add something or you'll not add something, but there's no negative quantity there.
there's no
There's nothing
negative.
negative
Okay.
there. And you're just
In that,
adding things with fractions, whatever, but you're just adding things. So whatever
sum of
you add,
non-negative
you'll.
number is non-negative like that.
Yeah.
Okay.
So now, remember, these were related to two actions. This was action C, and this was action quitting or to give an offer. So if you've reached a situation where the candidate comes with a state s equal to 0, you're never supposed to make the offer. That's what it means. You don't need to make the offer. You should let it continue. That is what the policy is telling us already. Hmm. Okay, so we're getting some information from here already. So mu t for state 0, the action to be chosen when state S is 0 at any given point of time should be to continue. That is the optimal here. That is the optimal by default, there's nothing else. Acceptable? So this is
Yeah.
part of the information we're getting. Now the next part is to focus on J1 JT of 1. There is a max that needs to happen. Notice these two quantities are the same, so I could just say that this is JT of 0. So now the comparison is between JT of 0 and T minus n. You can clearly make the argument that if T minus 1 is greater than JT of 0, that's when the action you'll choose, UT of 1, the one that you'll choose would be to quit. If it's the other way round, JT of 0, then you'd prefer to continue. If it's an equality, you can do either of the things, it doesn't matter. Right, this is just coming from the way JT of 1 is written. We didn't have to do anything more here. And this, in short, is giving us an action plan. This is telling us once a certain T is reached, a certain T is reached, beyond that T, you don't have to worry. Beyond that T, just choose the next best candidate. So, in other words, what this is telling us is the policy is this way. There is some specialty, or let's just denote it by tau.
Basically, T by N supersede the J of 0.
Yep. So whatever that is, let's say we have found a T, we have found a tau, a special tau. How do we find it? We'll get to that. But let's say that there exists one. So if our T is less than that, then what actions should we be taking? In case of state 0, the actions are by default. We're supposed to continue. There's nothing there. Uh, yeah, there's nothing there. But what about if you get the best candidate? Should you choose or not? Should you choose a candidate who is best by far?
For T less than tau, I'll continue.
You'll continue, right? So here, T less than tau, you'll continue no matter what candidate you see. So it means this is roughly saying that if you are restricted to choose only one candidate, you should observe you should observe the pool of candidates up till a few time steps. So the first few, don't make a decision, which is what this is suggesting. And then as soon as you hit this at time t equal to tau or greater than tau, actually even at equality, let's say it's continue only, if you see, if you've reached a candidate which is after tau, then you can stop at any one of them for which you get the state as 1. So the best candidate so far, you can just choose any one of them. So this is where you would quit. This is the only situation where you would quit. Otherwise, the optimal thing is to continue. Okay. So okay, now in the interest of time, I'll not go through the proof, even though I have it written out here. It was there in the notes also. Um, Unless you have doubts, I'll skip that part and just focus on what it was saying. Okay, so in this example, what we are seeing is it's giving us an optimal policy of how to deal with different situations. Different situations meaning which states are encountered and at what time step also. The policy shifts depending on where we are in the policy. Now, this is very similar to the behavior that is seen in multi armed bandits also. That you should explore for some time and then you should start picking the best arm. I'm just making a comparison of the idea, nothing more than that. MDP is a special class, multi armed bandits is a special type of MDP only. So, it's fair, this type of an idea should fit there also. That's about it. If you're not aware about what are bandits, don't worry. Okay? So now, as a part of proving that this actually is the optimal, we have only made rough arguments so far. If we were to formally prove this, that also can be done. And which says that at time t greater than tau, you should be, you could quit for any of the good ones. To do this, they've made simple comparisons between uh, these values, the value of j tau minus 1 for state 0 and state 1, and they've managed to reach at this point. um, Core point to take from here was, now if you look at the way j has been defined, for state s equal to 0, it's fine. Oh, acha, this is still a part of the proof only. Okay, anyways, the point is at the end of the proof, this proof also talks about what should be the rough value of tau for which, or any t greater than 0 for which this would happen. For which you would be in a situation where you should quit. This scenario basically means you should quit. This means jt of 1, the max of jt of 1 is this. Sorry, this is when you should continue. So you should continue for roughly 36% of the whole data that you're seeing. Beyond that, choose the best one you want to choose. Okay?
Yeah, okay. Just a funny thought. So, can we say that 37% NPTEL course I should consume, then decide to quit or not? Like we can apply.
I am not making any comments on that. No one
But
will.
but this is very famous problem I've seen in my BTech time for probability wise. Like there is a good YouTube channel number of file where like there are infinite toilets and you have to select like you have to reject some toilet to decide the best toilet. Like there are good YouTube and answer was 37% only.
I think it's coming in the same way. It's what you're describing probably is a stopping problem and defined, modeled in the same way that we've talked about. So it's possible that you can think of it that way.
Yeah.
If you have noticed, the way courses are structured, they're structured in a similar manner. It's one third, one third, one third of the courses, typically.
And after one third they'll ask about the exam registration. Makes sense.
Makes sense, exactly. So that's, they're giving you enough time to make up your mind, decide whether you want to continue, whether you think this is useful, and then it's a bet you made, and you're like, okay, let's see.
Nice. Mark of decision process in NPTEL.
I hope they don't hear it. Okay. All right. I'll come to the other one. So this was linear quadratic system. Remember earlier in the very beginning of today's class, I said the inventory problem that we saw comes under one of the umbrella. It was this one. It comes under this one. You recall the inventory problem had a xk of this form, xk plus 1 of this form. uk uh, wk was the random demand, so it was this. And backlogging is allowed. This is just one example. Here, this is talking about examples of this kind in a more general setting. The There are constraints to the problem, but the setting is overall very general. So what they're saying is, let's say xk is of this form. So xk's or xk plus 1s, these are some vectors. The dimensions are appropriate, as in you could take a particular dimension of xk and hence a, b and so on would have to be rectangular matrices of a certain kind. So you could have those transitions if that's what you wanted to do. So none of that needs to be restricted upon from the beginning only. And then there is wk, which is some noise. So there are two conditions on this noise. The conditions are three conditions, sorry. The first one is that it is independent, meaning wk and wk minus 1 or any wk and wj are not related to each other. And second is the mean is 0, so the noise has no mean, but the covariance is finite. This is it. These are the only conditions on wk. And the goal of the problem is same stuff. Let's say we have a quadratic function now. This is uh, this the type of the function, the type of the cost that you're trying to minimize. This is fixed here. The form is fixed. It has a quadratic form. So now when we talk about linear system and quadratic cost, this is a problem that is very nicely solvable. This gives closed form solutions, and this is something that has a lot of applications in many different areas. This is one of the most widely applied model that comes from these types of systems. Okay, so in such a problem, oh okay, I forgot to mention a few things. So here, yeah, right, this much I have already said. Xk's and uk's are some vectors, ak's and bk's are some matrices. They have to be appropriately chosen, that's all. Wk is also again some vector. Now there is just two constraints. One constraint is on this q, and the other is on r. So q has to be positive, qk has to be positive, semi definite, rk has to be positive, definite. And a simple reason why these conditions are placed is because we are minimizing. If we don't put some constraints on these um, matrices, the this would become an unconstrained problem, and we'd not get an optimized value. It'll become infeasible. It'll give us minus infinity and so on.
Yeah, correct.
So
But
we need
RK
something.
should be RK could be positive semi-definite, right? Why it should be definite?
I think there is a reason for that. I am not fully sure as to why it has to be positive definite. It could possibly mean that we don't want the cost or reward because of choosing an action to completely go away. So
Basically,
that's one possible way of
if
saying it.
UK is zero, so there will be chance like it is zero only for UK.
No, no,
RK,
UK is a matrix.
yeah.
So it's just
Okay.
saying that for no matrix, they would want the eigenvalues of this quantity
Mm-hmm.
to be 0. Basically, this should have some effect in the optimization, because we're optimizing over this. Otherwise, there's nothing to optimize. There's nothing here that is getting optimized. xk's are chosen, the next state is chosen based on the previous one, but it's the action that chooses that. So here it's inside, it's hidden to us, but here it's in the most explicit form that there is. That is the only reason I can think of why it's not semi definite. Maybe the reason for this might come up in the upcoming lectures. If not, I'll try and think of a reason why this is not, why this has to be positive definite and not a positive semi definite.
Because it's a tighter constraint, right?
It's a tighter
Positive
constant.
definite.
Yeah. Okay, so all right. There is one more class of problems within this. What is it called? Linear system and quadratic cost type problems. That is called quadratic regulators. But never mind. That's not what we are focusing on. So since we have very limited time, let me just brush over the idea that was talked about. So, so the same DP algorithm can be applied here also. So what that tells us is that we're supposed to start with the terminal cost, and the terminal cost is taken to be this. Xn's are the terminals, not written, but t equal to n is the time horizon. Again, it's the same kind of setting. That part is not changing. Okay, then in the next time step we would be interested in optimizing a quantity like this, right? This is the stage wise cost of that particular xn, and choosing the action un, and the value function from the previous step for the particular state. Okay, my for this. So in principle we could write it out and simplify this. This process was done in the lectures, so for now I'm gonna skip that part. You can see that those steps are actually very straightforward and easy to follow. Once the whole process is done and you try to actually optimize it, meaning to find the minima of this quantity, you take the derivative with respect to mu n minus 1, u n minus 1, and equate whatever gradient you get to 0 and simplify that. And after you simplify that, what you would get is, so I'm skipping a bunch of steps, what you would get after you simplify, as in after you've optimized this already, is you would get some u n minus 1, the star one, would be something that is linear in x. So what next state should be chosen, or whatever is the current state, that decides what action should be chosen. And there's some ln minus 1 which depends on things like r, q, a and b. You can find out what that is. That's fairly straightforward to do. Next thing is, if you plug this in and try to find the optimal value, you'll see you'll get some quantities which are quadratic in xn, xn minus 1. The middle factor would be a bunch of terms once you simplify all of them. So let this just be called kn minus 1. This is called k because it's called the uh, it comes up in the theory of Kalman filters and all of that also. This one is called the Kalman gain. This one, the equation that comes up here is, no, not this equation. The k, what exact form of the k it is, not k in general but kt, that is called Riccati equation. Anyway, so what you get is something quadratic in x, and when it is quadratic in x, everything, all the u's, everything is already put in here properly. And then there is one extra term. And that one extra term is this one. But notice there was no effect of the noise when the optimal policy was getting chosen at time step n minus 1.
It was R or it was K.
In general, it is k, it is depending on whatever it is. But here, for the first one, it is going to be r only.
Okay, okay. R or Q?
Ha,
I
right,
think
q makes more
Q.
sense. Q of n, because it's the previous one.
And since it's a positive semi-definite, this will be positive number all the time. And we are minimizing it, so there is no impact of adding positive number. It's an offset.
Correct. But this is the importance here is the effect of the noise shows up in the optimal value, but it has no effect in the policy itself.
Because it's a positive number, and but if it is somehow become negative, it can have an impact.
No, that's not the main part. The main part is this noise is not dependent on anything. If this noise had some correlation with x or some correlation with u, then it would show up. Then its effect would show up in the policy also.
Okay, okay.
Because there was no such correlation, that's why a lot of these terms simplified very nicely. Some of them cancelled, some of them became zero and not meaningful. Basically, if there was just one this, then it cancelled. Okay, now if this process is repeated, so this is only for n minus 1. If this process is repeated, then, okay. Okay, this is what kn minus 1 is. I am not interested in remembering these things. If you are, it can be solved in a fairly simple way, but yeah. Oh, okay, right. One thing that I had to point out here. Now, because of the quadratic form, we started with a quadratic form, remember? And we again have something quadratic in x only with additional covariance term. That term is fine, but we started with something quadratic, meaning something, it was a convex function in x. We still have a convex function in x. So this process is still giving us a convex function, and the core reason why this is actually happening is because this kn minus 1 ends up being a semi-definite quantity. You can verify that that is the case. It clearly looks symmetric, so you can verify that this is actually semi-definite also. Now, if this process is repeated for other time steps t less than n, you'd see the same behavior happening. It's just a recursive process. So every ut that we'd observe would be some function of some lt and x of t. And the optimal value would be similarly convex in xt, or just convex, or quadratic in xt and hence convex. And some extra term, okay, the covariance term. Now this lt and kt have specific forms, and you can derive and work with those forms. But the main point is, it's because of the way the problem has been defined, this these u's, the optimal actions, are independent of the presence of noise. And this becomes a very important factor in designing these things, and this is something that is used a lot in industry. In fact, okay, this stuff is not so important. In fact, they use this as a principle in even non-linear situations, even though it may not hold in non-linear situations. So what they do is, suppose they have a noisy system, they have a noisy problem. Instead of taking the all the moments of the noise, they only focus on the mean of the noise. Then they make it into a deterministic problem, which is the kind of problem that we had. Find the optimal policy, meaning even if this noise was not present, what happens in that case? Find the optimal policy. The optimal policy would be of the same form that we saw. And the claim is, at least in this situation, this optimal policy is going to be the optimal policy even in the noisy problem. So people use this particular idea, adding noise a little bit at a time and working around with the optimal policy. And this idea comes under the principle called certainty equivalence principle. So the class of problems where this principle holds would be something very interesting, whatever that class is, or if there is a simple counter example to situations where this doesn't hold. Even if so in the upcoming lectures, sir will talk about a very famous counter example to this, and that will be a linear example only with some catch obviously. But this, what we saw here, that just replacing the noise by mean of the noise is definitely not enough, because we know that one moment of information of any random variable is never enough. There are other moments also, unless the noise itself is such that it has only one moment which is meaningful and the others are of no meaning to define that distribution. In that case it's fine, but otherwise that's not the general scenario. So next time, this is what will be the focus, the certainty equivalence principle. There'll be more about this, these linear quadratic type problems. In fact, there'll be a particular subgroup of problems where these x's, and in fact even the noise maybe, they're taken to be Gaussians. So it becomes a LQG problem, and that's what will be talked about in more detail. Okay, so are there any questions or doubts?
No.
Okay, so let's quickly revise. So today we started by taking a recap of what was the DP algorithm, what it said and what it did. Then we looked at two examples today. One was in a lot of detail, that was the optimal stopping problem. The particular specific example that we talked about was the secretary problem. So in the secretary problem that we saw, the way it has been defined, we saw that after optimizing it, we were able to get a situation where we could say, for any given time step, for any given state, what should be the action taken next. So a complete optimal policy was defined. But like it is said, it is only possible to come up with such optimal policies in specific cases. Most of the times it's going to be approximations to that. Then we briefly talked about the linear system with a quadratic cost. Here again there is a very interesting phenomena that happens, which is that the optimal policy just depends on the state. It linearly depends on the state, and the problem stays convex because of the presence of this K matrix, which is a positive semi-definite matrix. And this is unaffected, this policy choice is unaffected by the noise. And this idea that policy, the optimal policy, is not affected by the presence of noise or what noise it was or what distribution the noise was coming from, is something that is used a lot under the idea of certainty equivalence principle. And whether this holds in general or not will be something that will come in the upcoming lectures. Okay, so I am done from my part. Um, if there are no questions, we can end here.
Yeah, thank you.
Yeah. Okay.